In this video, we're going to look at types of organic reaction, how we can spot whether something is an addition, a substitution, hydrolysis, condensation, and also how we can spot the mechanism of the reaction just by looking at the balanced equation and the type of reagents involved. So, in organic chemistry, how do we recognise types of reaction? There's loads of types of reaction that you might have already come across, and if you haven't come across them yet, you're almost certainly going to come across them in your A-level course. So we have addition, we have substitution, and we're going to go into those two in a lot more detail. We've got condensation, which you may not have covered yet, but you may have covered at GCSE when you did making esters. We've got hydrolysis, elimination, and then of course there's oxidation, which we were talking about last week, and the converse reaction, reduction. Then we've got hydrogenation, hydration, and dehydration. Those last three are just very specific words in terms of either adding hydrogen, adding water, or removing water. And in fact, all of those last three come under one of the other types of reaction as well. So just a brief look at oxidation and reduction, because actually we're going to look at that in a few days' time in more detail, because it's a very common, quite detailed reaction that you have to cover. So we've done redox in terms of ions gaining and losing electron, and we've also talked about oxidation number. And then in the organic section, you'll be looking at oxidation in terms of primary or secondary alcohols, making aldehydes or ketones, and maybe carboxylic acids. And as I said, there's going to be another video to cover those. But in terms of organic definitions of oxidation and reduction, we can kind of go back to our basic ideas of addition of oxygen. But if you look at this example is not actually adding oxygen to the molecule itself. So there is oxygen present, but what the oxygen does is actually removes hydrogen from the OH group and from the adjacent carbon. So removal of hydrogen is also oxidation. Simple reason for that. Oxygen has a -2 oxidation state, so if you add more of something with a -2, the carbon needs to become more positive. Hydrogen has a +1 oxidation state in compounds, and therefore if you remove hydrogen, then you are removing something that is positive, and therefore the carbon itself is going to have to become more positive in order for the compound to stay neutral. The other way of looking at it is that when you remove that hydrogen, although you're not adding oxygen, you're increasing the number of bonds to oxygen. And so oxidation can also be thought of as simply carbon making more bonds to a more electronegative atom. We're going to consider condensation, hydrolysis, and elimination all together and compare the similarities and differences, because they are quite easily confused, and especially if we haven't done much on condensation yet. So don't worry if you haven't done condensation yet, although most of you will have done it at GCSE. Condensation can be considered the joining together of two molecules by the loss of any small molecule. So one way we're often taught to remember condensation is the formation of water, which is true, and so we're linking it with this idea of condensation on windows. However, it doesn't need to be water, so it can be any small molecule that's lost. For example, if the carboxylic acid had a chlorine there instead of an OH, so if it was an acyl chloride, it would make HCl. There's our example. So you can see that we don't need to be losing water, it can be HCl instead. But the point is that we're joining two molecules together. That is the key aspect of condensation, and we're doing it by losing a smaller molecule. Okay, what about hydrolysis? So hydrolysis literally means the breaking of bonds, hence the lysis. So lysis means breaking. You may have heard of photolysis, breaking bonds with light. And then hydro just means using water. So it's the opposite of condensation most of the time. And when you are doing things about carboxylic acids and esters and their reactions and amides, you will be looking definitely at hydrolysis being the breaking apart of two molecules, or one molecule to make two. So it's considered the opposite of condensation. Although we're using water to break the bonds, so you can see that we're adding an H to one side and an OH to the other, hydrolysis is usually quicker in the presence of an acid or an alkali. Okay, so both of those work to speed the reaction up. So you may just be told that something is added sodium hydroxide or you've added sulfuric acid. Don't be confused there. Don't try and put those necessarily in the equation when you're working out the products. We are just breaking bonds by adding water, by adding H on one side and OH on the other. But hydrolysis doesn't have to mean exactly the opposite of condensation. So condensation is always joining two molecules together, such as a carboxylic acid and an alcohol. But hydrolysis doesn't mean that, doesn't have to mean that, because it's just bond breaking. So nucleophilic substitution of a halogenoalkane with hydroxide ions is also a hydrolysis reaction. You could write that in form of adding H2O, and you can look at that in the video about mechanisms. So because we're breaking a bond using water, essentially, we're adding OH to one of the substances, then that is also hydrolysis. It also doesn't have to be limited to organic reactions. So you may have come across something called POCl3. That is sometimes used as a test for OH groups in some syllabuses, but you can see that we're breaking the PCl bonds, so the chlorine is leaving the molecule and OH is going on to the phosphorus. That's what's happening there to make phosphoric acid, and the H part of the H2O is going on to the chlorine. So this time we're not necessarily splitting two molecules apart, but we are breaking the phosphorus chlorine bond using water. Elimination is the removal of a small molecule. So we've got a small molecule formed again, like condensation, but we are not removing a molecule to join molecules together. We're removing a molecule to join two carbons in a double bond. So you may study this in terms of adding, instead of aqueous alkali to an alcohol or a halogenoalkane, if you add alcoholic alkali, so concentrated sodium hydroxide in the presence of an alcohol, then this will happen instead of substitution. And you may have also covered dehydration of alcohols. That's done in the presence of an acid. So this reaction is very similar to condensation and hydrolysis in that it's catalyzed by acids or bases. It's really just rearrangement of hydrogens and oxygens in molecules, removing OHs, adding OHs, removing H+, and adding H+. That's what's happening in all these molecules that makes them very, very similar. And so the reason that the base works, you can see a little mechanism there on the right, is that, for example, you could lose X, which would be a halogen. You could have a halogen leave, which leaves a positive carbon. The electrons can come away from the H+, because the H+ gets accepted by a base. You may need to know that mechanism, but it's likely that you don't, because it's quite niche in terms of exam boards. Either way, elimination is simply the opposite of an addition reaction. In an addition reaction, you take an alkene, you add a small molecule to make, for example, an alcohol or a halogenoalkane. In the elimination, it's the opposite way round. So really, the main types of reaction that you're going to have to identify are going to be these two. And the reason these two are going to come up, addition and substitution, is that these two are the ones that you need to know how to do curly arrow mechanisms for. So within these two types of reaction, there are three mechanisms by which addition or substitution can occur. So usually they don't differentiate. Usually it's a 2-mark question that says, give the type and mechanism of this reaction. Or give the full name for the type of this reaction. And because it's 2 marks, you know that you either need the word addition or substitution, and you also either need the word electrophilic, nucleophilic, or free radical. So how can we tell the difference between them to make sure that we get the right type of mechanism, especially if we've spent a long time learning it, so we don't get confused? Let's have a look at our definitions for those 3 different types of reagent. An electrophile is an attracted to an area of negative charge. In a sense, that means a carbon-carbon double bond. It just doesn't mean anything else in the organic chemistry that we study. Not enough to say that it's simply attracted to it, because it doesn't just get attracted to it and then go near it. For example, a water molecule will also get attracted to an area of negative charge, but it doesn't do anything if it goes towards a chloride ion. So what we really mean is that when it gets there, it accepts a pair of electrons from that area of negative charge, forms a new bond. Electrophiles do not have to be positively charged, and I'm not going to look into what types of molecules are electrophiles for reasons that will become clear when we actually try and identify electrophiles in reactions. So nucleophiles, bit of a spoiler there down in the bottom right, are attracted to areas of positive charge, which means they can, of course, be negatively charged. When they get to that area of positive charge, which is actually going to be a positively polarized carbon, then they'll donate a pair of electrons to form a covalent bond. So they can have a negative charge. Those examples down there, hydroxide, chloride, cyanide, which you may not have come across yet, but you will. But they don't have to be negative charged, but they must have a lone pair because they must have an excess of electrons that they can donate in order to form a covalent bond with that positively charged carbon that they're attacking. And anything that can be a nucleophile, for example hydroxide, can also behave as a base, such as also ammonia. And hopefully we know what bases are by now, and that's because they do the same thing. When they act as a base, they use their lone pair to donate and form a dative covalent bond, a new bond with a hydrogen ion. So instead of attacking a positive carbon in the sense of a nucleophile, when it's behaving like a base, it accepts H+ instead. Ligands, depends whether you've done any transition metal chemistry yet. If you have, you'll know that molecules with lone pairs can also form dative covalent bonds with transition metal elements. So bases, ligands and nucleophiles are all part of the same story. It just depends what they're reacting with as to how we define them. There's our other 3 examples just to prove that we can have nucleophiles that have no charge on them. Water is an excellent nucleophile, as is ammonia, and amines, if you've come across amines yet. Free radicals. They're kind of the leftover species. Their mechanism is very different. We don't tend to have to draw curly arrow mechanisms for free radicals. It's a species with an unpaired electron, so anything that has an odd number of electrons. It's extremely unstable, which means it will react with anything. It doesn't really matter what functional group you put a free radical with. It will just react. It will just form a bond. It's not accepting and it's not donating electrons. It's donating 1 electron and gaining 1. And so whatever it reacts with is going to leave behind an unpaired electron as well, unless it reacts with another radical. So how do we know, just by looking at a reaction, what type of reaction it is? So we can have a sort of 2-mark question that says, what type of reaction is this? Is it addition or substitution? And having identified that, is it nucleophile, electrophile, or free radical? So here's 5 reactions that I've deliberately made very samey. And I've also deliberately just given structural formulae, so they're a little bit harder to unpick. So first thing with these 5 reactions, are they additions or substitutions? This is the bit that people get a lot easier just by looking at the balanced equation. It's as simple as, if there is a second product, then we must be talking substitution. Addition means two molecules coming together to make one, and therefore there's only going to be one product for an addition. The other way I know is that addition happens in the presence of double bonds. If we look at the two things that are addition reactions, they are C2H4, so they are alkenes. So that's how I find additional substitution. So far, so easy. But how do I identify nucleophile, electrophile, or free radical? A little bit more challenging. And the reason it's challenging in this example is because people tend to try and look at the reactant on the right. They try to look at the chlorine or the HBr or the H2O, but as you can see, those molecules come up time and time again in different reactions, and they don't behave the same way. So especially when I'm trying to identify an electrophile, I can't tell whether chlorine is being an electrophile unless I know what it's reacting with. So instead of looking at the reagent that you add to the organic compound, when you're deciding whether it's nucleophile, electrophile or free radical, you look at the organic compound. What is it about the thing that contains carbon that would induce a reaction to happen via the three mechanisms that we know? So first of all, let's go back to our alkenes, because we already know they undergo addition reactions. Well, it turns out that alkenes undergo electrophilic addition, and that is the only type of addition that they undergo. And that is because they have got a high density of electrons in the carbon-carbon double bond, and that is what's going to attract whatever reacts with the alkene. So it does not matter whether it's HCl, H2O, Cl2, Br2, etc. It's always going to be an electrophilic mechanism. Possible examples where it might not be that would be where an alkene reacts with itself, or where an alkene reacts in the presence of a catalyst with something like hydrogen, very slightly different. But you're not going to be asked to draw the curly arrow mechanism or name the mechanism for that reaction, so don't worry about it. Okay, going back to our molecules, we've decided alkenes all undergo electrophilic addition. What else do we have present? Well, I'm going to select these two compounds now. They're not the same compounds, so we've got an alcohol and a halogenoalkane or a haloalkane, depending how you want to describe it. But what they do have in common is they both contain an element other than carbon, so oxygen and bromine, or an element other than carbon or hydrogen, which means they have a polar bond. And if they have a polar bond, it means that one of the carbons in those molecules will be positively polarized. And so any molecule that has a delta positive carbon will undergo nucleophilic mechanisms. Notice I've not actually said nucleophilic substitution. These molecules will be nucleophilic substitution, and these are molecules that you've already come across. And the reason they'll undergo substitution is because they are saturated and only contain single bonds. So in order for anything to attack the delta positive carbon, something needs to come off that carbon. If you haven't looked at it already, you'll be looking at the reactions with C double bond O next year, and sometimes they can undergo nucleophilic addition. It's addition because it's a double bond, but it's nucleophilic because it's a positively polarized carbon that is being attacked. So again, I don't need to look at what they're reacting with to know that that will be a nucleophilic mechanism if I'm asked for the type of reaction. So what are we left with? We've looked at alkenes, and we've looked at alcohols, and we've looked at halogenoalkanes. So the only functional group, if we can call it that, because it's not very functional, is the alkanes. And so, well, the alkanes have got no real incentive to react, which is why they're very unreactive molecules. They have no delta positive carbons, and they have no carbon-carbon double bonds, so they've got no area of electron density. And so if they've got nothing to incite a reagent to react with them, then the only thing that alkanes will react with is free radicals. So alkanes undergo free radical substitution. It's always substitution because alkanes are saturated. It's free radical because there's nothing else other than a free radical that would possibly attack those non-polar bonds with no carbon-carbon double bonds. Even reactions that we don't think of as having mechanisms like that would still be going free radical mechanism. So even combustion, you have to break bonds in order to get combustion to go. It's got a very high activation energy, and that would that would be a radical mechanism, but we don't have to know about it, so that's fine. So it does mean that actually you will cover all of the possible combinations, so of the different types of reaction with the different types of reagent. So we should have already done free radical substitution. That's our alkanes reacting with halogens. Also comes up with CFCs and reactions of those in the ozone layer. Then we've got electrophilic addition. So that is our alkenes because they have a carbon-carbon double bond. They're going to undergo addition because of the double bond, and it's going to be electrophilic because it's attracted to the electrons in the double bond. Nucleophilic substitution, that's our alcohols and halogenoalkanes. Saturated molecules, substitution. Delta positive carbon, therefore nucleophilic. And then if you haven't already done them, you'll also look at electrophilic substitution. That's with aromatic compounds, so they technically have carbon-carbon double bonds, but the electrons are delocalized, so they're very stable, so we don't add across them. Then we have nucleophilic addition, which I already mentioned. So carbon double bond oxygen, it's polarized, so there's a delta positive carbon, hence nucleophile. It's a double bond, so it can be added across, hence addition. Free radical addition isn't really going to come up. You're not going to be asked for a mechanism of that unless it's a sort of extension question, maybe in OCRB, where you have to read an advance notice piece of material. But polymerization of alkenes is actually free radical addition. It's addition because it's alkenes, and we're obviously adding to make the polymer. It's free radical because if you think about it, an alkene can't be an electrophile itself. So an alkene can't be attracted to another alkene, and therefore it's actually a free radical mechanism that gets that going. And that's all we need to know.